Welcome to EcoCommons, the platform of choice for analyzing and modeling ecological and environmental challenges. My name is Emilia Decker, and in this module I will show you how you can visualize your data in R and turn data like this into a beautiful graph like this. All using a free high-performance computer in the cloud, so you don't have to burden your personal computer. Here at EcoCommons, we empower students, researchers, and decision-makers to protect and restore the planet by drawing on the immense expertise of our partners, collaborators, and top scientists. We provide access to ecological and environmental data, robust scientific workflows, and digital infrastructure at your fingertips for free. You can learn how to quickly turn noisy data into high-quality results in an easy-to-use point-and-click environment, or brush up on your coding skills on the cloud. If you're an early researcher, student, educator, or policy decision maker with keen interest in ecological modeling, EcoCommons is for you. EcoCommons will help you to spend less time data wrangling and configuring models and more time on restoring and protecting the planet. So let's have a look how we can visualize the data in the R environment on EcoCommons.
If you have watched the first module on how to manipulate your data, you can skip 6 minutes ahead. If you haven't watched the first module, keep watching and I will show you how to set up your working directory and get ready for this module. Once you're signed in, click on Analysis Hub and then Coding Cloud. Click Launch Notebook Server and then choose the EcoCommons R environment, which includes the RStudio image. Let's open. Then click on the RStudio icon. This will open RStudio in the cloud. Once you downloaded the R script from the website, you can upload it here by going to Upload and then choose where you have saved it. Now we can open the R script. This is the complete script of both modules. The first module was manipulate data, and the second one will be ggplot, which I'm going to go through today with you. So if you didn't have a look at the first module, I would recommend you to run a few lines of codes before. So we definitely need the library tidyverse. So let's highlight that. And we can either press Run up here, or we can press Command Return if you're on a Mac, or Control Enter if you're on a Windows. So now we have loaded the library tidyverse. Next, let's set up the workspace. Again, we can highlight that code, press Command Return, Control Enter, or Run. Now our working directory is set, and I would recommend to run these 3 too. So we will have a folder with the raw data, a folder with the results data, and the folder where we put the figures in. In the first module, we downloaded the raw data and we created data that we are going to use today to visualize it. So as you can see here, I already have those 3 folders. If you don't have them, run these 3 lines. Next, we want to download the file that we used in the first module, just so we can manipulate it a little bit to make it easier to visualize later on. Just run the download code, and what it does, it's a command, a function that says download.file, and in brackets we're giving it the URL, which is on Figshare, this one, And then the argument dest file just says where do you want the data to be stored and what it will be called. So in this case, we want to save it in the data raw folder, and we call it portal_data_joint.csv. Once you run this piece of code, you can see in the data raw folder that you have downloaded it. Next, what we want to do is to read the CSV file in. And very important here is to use the function read_CSV and not the function read.csv. That is just because those two functions read the data in just a little bit different. But we want to, because we're using the tidyverse package, we want to use the read_CSV to make sure the data is proper read in. So let's run this piece of code. Now what we can see is that we have created an object that is called surveys, which is a data frame with 13 columns and over 34,000 rows. I won't go too much into details here, just because we covered this in the first module. So the last thing I would like to do, so we're all on the same page, is to clean the data the way we did in the first module to make sure we will not run into any problems later on. So to clean the data, just at the line 208, if you highlight that to 218 and press run, what we can see is that we have created two more objects. And if we go into our data folder, we can see that we have created another CSV file. And this is the data that we will use to plot and to visualize. Now let's have a look at ggplot2. Let me first zoom in a little bit. Here we go. So ggplot2 is based on the grammar of graphics and has three essential elements: the dataset that we just created, then the mapping of aesthetics to variable that we get from the dataset, and the geometry. The basic ggplot template looks like this. We have the function ggplot, and the reason it doesn't have a 2 is because ggplot was refreshed to ggplot2, but the function itself stayed ggplot. So in this function, the first argument is our data. So data equals then the dataset that we produced, then mapping, and then aesthetics, which is AES for aesthetics. We name the aesthetics the X and Y axis, and then the geometry function or geom function. So let's start with just plotting the dataset. So if we say function ggplot and then put in our dataset that we created in the first module, and then press Command Return if you're on a Mac, or Control Enter if you're on Windows, or you can also press this button Run. What we can see is that R has now created a blank canvas, and that is because we haven't given ggplot either the aesthetics nor the geometry. So it just says, well, we have a canvas, but you didn't actually tell me what I need to print. So in the next one, let's put some aesthetics in. Here, that is the argument mapping equals aesthetics. And we want on the x-axis the weight, and on the y-axis the hindfoot underscore length. So let's run this code. So what we can see now is we have the y-axis hindfoot underscore length and the x-axis of weight, but we still don't have any points, and that is because we didn't put any geometry in. So let's present the data with and add points. So we add a geom function, and in this case the argument would be geom underscore point. So the data will be presented as points. We run it, and now we can see all the data points on the y and x-axis. This is not very pretty or useful to us, but this is the basic, and building a plot is iterative. So you start with the data set, and then you put an axis on, and then the geometry, and from then on you start to modifying your whole plot and add more information. So for example, let's put some transparency in this plot to see where the points are actually have a high abundance. And to add transparency, we put in alpha equals 0.5. So alpha is the value for transparency. And what you can see here in this function is that I don't write data equals anymore, and I don't write mapping equals anymore. And that is because R is smart, and it knows the first argument will be the data set and the second one will be the mapping. So you don't have to write it. And if you're like me, I'm a bit lazy when it comes to writing code, so I take any shortcut that I can get. So let's run this little bit and add transparency. And now we actually see a little bit more of the distribution. We can see it's concentrated here in these very, very dark areas, but actually spread out quite a bit everywhere else. We can also change the color of the dots and the transparency even more. So let's make these points blue. So the argument for that is color equals blue. We put that in the geom underscore point argument. If we run this piece of code, I'm using command return because I'm on a Mac, and we can see we created the same plot but in a different color now. And I will give you some links to good resources that will show you the different types of color that you can use in R, including colorblind friendly options. Now let's say we want each species to have a different color. We can do that as well. For that, we just use the argument aesthetics in the argument geom underscore point, and we say choose the color according to species ID. And we can see now we have different species and different colors for each species with the little scale on the side. Great, I guess it's time for a little challenge. Can you figure out how to create a scatter plot of weight over species ID with plot type showing different colors? If you want to give it a go, pause the video. Otherwise, let's continue. Okay, so let's create this plot. So we use the function ggplot, and our dataset surveys complete. And let's put some aesthetics in. On the x-axis we have our species ID, and on the y-axis we have our weight. And let's put the aesthetics of the color in here. So it doesn't matter, as you can see here, we put the color in the geom function, but we can actually put the color up here. And then we save at least these 3 letters. So let's put color equals plot underscore type plus geom underscore point, and let's run it. There we go. So now we have species ID over how much it weighs in each plot type. Again, not very pretty, but basic, and we can work from here on. The easiest way to work with plots and try different geometry functions is actually to put the plot into an object and then try different geometric functions with it. And what I mean by that is, for example, here we say survey plot, and that is going to be our object, and we say put the data of the surveys complete in and use on the x-axis the species and on the y-axis weight. And you can see again I shortened the whole code a little bit more, so R knows that the first argument in aesthetics will be the x-axis and the second one the y-axis, so we don't need to put y equals weight anymore. So if we run this code, let's make this a little smaller again, we can see we have now the object surveys plot, and we can try different geometrical functions here again. So for example, let's say 1 point, and the color should be plot type. That gives us exactly the same plot that we had before. So this one up here in our challenge. Let's try a box plot. So again, just use the object that we created and just use a different geom function. In this case, geom underscore box plot, and that will give us a normal box plot. We can also add multiple geom functions together. So for example, if we want to see the box plot and the distribution, we can put box plot plus geom underscore jitter, and we say the transparency should be 0.3 and the color, let's call it tomato, that would be a funky red. Okay, let's run this code. And I'm using different times run or command return, just so you can see you can use both functions, both options. What you can see now, we have the box plot, which is behind, and then the jitter plot on top to see the distributions of the weights. Okay, so this is not very nice, and we can't actually see the box plot, and that is because we put the box plot before the jitter plot. So if we want to be if we want the box plot to be on top of the jitter plot, we just need to put the jitter plot before the box plot. Okay. And as we can see now, we have the jitter plot and the box plot on top. And box plots are not very handy. They are used in scientific publications, but they don't really tell you much about the distribution, and that's why people started to use what is called a violet plot, because they show the distribution or reflect the distribution just a little bit better. And to show you what I mean, let's just run the same plot but with the geo_violin function. There we go. This is again not very pretty. This is just one big line, and that is because the scaling is not quite right. And what we can do is we can actually change the scale of the axis that reflect the distribution just a little bit better. And to change the scale of, for example, the y-axis, so we use scale_y_log, and that will scale the y-axis on a logarithmic scale. Again, we have our object that we created before. We say give us the violin option and scale as well. So once we can scale it, we see the distribution just a little bit better. Great. Let's talk about time series. Let's look at the counts for each genus per year. First, what we need to do is to calculate the number of counts per year for each genus. And for that, we can use what we learned in Module 1 and create an object called yearly_counts. And we say go to surveys complete, the data set, and then count the year and genus. So let's have a look at the object that we just created. And we can see in the year 1977, this genus was counted 3 times. And we have that for all the years and all the genera. Okay, so now we can plot the counts of genus over time. And for that we use ggplot, our function. We say go to the data frame yearly_counts, use the aesthetics year on the x-axis, and on the n is for counts on the y-axis, plus give us the geom_line function. So we want lines. Again, not much information here because all the genera are together and not separated. So we want to separate them by color now. And similar to above, we use the ggplot function, our data frame yearly counts, our x-axis is the year, y-axis is n, and we say separate everything by genus. Use color to separate everything by genus and give us the lines. Great, so now we have the counts of each genus per year, and we also have the legend on the right hand side to see which genus is actually which color. Another option for this is we could put the color in our geom function, like I mentioned before. So it doesn't matter where you put the color in, but I can run this code so you can see that it really doesn't matter. It's more, you use a few less letters if you put it up there. We can also include the pipe operator to create a graph. So we could say go to yearly counts, and then plot the yearly counts under the aesthetics year on the x-axis, n for count on the y-axis, separate each genus according to color, and put it in a line graph. Again, we have three options. It's up to you which one you prefer. We can use the pipe operator also to link data manipulation with data visualization. So, for example, here we can create a new object that is called yearly counts graph. We just assign it the surveys complete data, and then, so we say go to surveys complete, and then using the pipe operator, count year and genus, and then plot aesthetics. On the x-axis you have year, on the y-axis you have the counts. Separate the genre by color and give us the graph in lines. So what will happen when we run this is that we created a new object here that is called yearly counts graph, and in order to look at this graph we actually need to run this. So let's highlight that and run it, and we have again the same graph. So this looks already a little bit better than the previous graphs with which we started, but we can do actually much more with ggplot, and one of my favorite things to do in ggplot is called facetting, which it splits the plots in multiple. So you have one plot, but you can split it in multiple based on a factor that is in your data set. And I can show you how it's done. So have a look at it. Go to yearly counts, the object that we just created, and split that one plot into multiple depending on genus, the factor genus. So you can see now, if I make it a bit bigger, this looks way prettier than before. So we have, for each genus, we have a separate plot over time, with the year being on the x-axis and the counts on the y-axis. What if we don't want to have such colorful graphs? We can also make it so the graphs don't have different colors. For that we say ggplot, go to the data frame that we created called yearly_counts, use year and count on your axis, give us the geom line, and then wrap it up according to genus. Here we go, and now everything is black. But that's not all we can do. We can also split each graph depending on the sex. So we have male, female, and undetermined. And we can actually split each of these according to male and female. So here we have yearly. So first of all, we need to create that data set, so R knows where to look for. So let's create an object that is called yearly_sex_counts. We go to surveys complete and then count year, genus, and sex. So let's have a look. And now what we've created is, for example, for the year 1977, the females of this genus were counted 3 times. The females of this genus 103 times. Males 119 times. and so on. For each year, each genus, each sex, we have the number of times that animal was caught. Okay, now that we have the data frame, let's have a plot for this. We go to ggplot, go to yearly underscore sex underscore counts, and for the aesthetics we want the year. The y-axis is our counts. We want it to be separated by sex. We want it to be a line graph, and everything to be split according to the genus or according to genre. Here we go. So now each plot is according to a genus, has a female and male. We can also facet both by sex and genus. We just need to use facet underscore grid instead of facet underscore wrap. And then we can use two variables. So for example, let's use sex and genus. So we have ggplot, and then our dataset yearly sex count. On the x-axis we have year, on the y-axis we have n. We say give us a line graph, and then we want the rows to be sex and the columns to be genus. So now we have females for each genus on the top and the males on the bottom for each year. And this doesn't look pretty, but we will get to that very soon. We can also include colors. We can say have the colors be different for each sex. We can also swap rows and columns if we want. That's just your preference. So we say the rows should be genus and the columns should be sex. We can also have one column and facet by rows. So for that, we just put the rows in and not the column. So now we have the year, the count, and each genus is now basically a plot, one on top of the other, or one above the other. Doesn't look very nice, does it? We can also have one row and multiple columns. For that we just put the column argument in the bottom instead of the row one. I still find the first plot the nicest of them all, so maybe let's go back to that. And I can also show you a nice little trick that is called theme, which is a pre-loaded themes that really amazing people just created, because ggplot is very, very massive and you can modify your graph as much as you want with every little detail you want. You can make the background colors different, you can make the headings different, the axis different, the numbers, how bold the color, how far away it is. But it takes a lot of time and a lot of knowledge. But some people already created what is called preloaded themes, so you don't have to do as much anymore. And what those themes look like, let me give you a little demonstration. Let's go back to our previous graph. So ggplot, the function, we have yearly underscore sex underscore counts as our data set. We want on the x-axis the year, the count on our y-axis separated by sex, or the colors should be different for the different sex. We want it to be wrapped up by genus, and we want a theme that is called theme underscore BW for black and white. And now you can see the background is lighter than before. We have different headings for each plot. It just looks a little bit cleaner. There are many different themes, and if you want to choose a theme or look them up, just type $theme. You can do it quickly. Let's go theme. That gives us the help, and this is what theme uses. Lots and lots and lots of arguments. And we have different spacing, a lot of explanation if you want to go down the rabbit hole. This is where you can look at. You can also Google what each theme looks like, or you can just play around here. For example, I played around a little bit and called it a theme light. So let's have a look at the difference. Yeah, that looks lighter than before. So if we just click on this arrow, we can look at the different plots. There's more black around the boxes. And this is definitely a bit more lighter. Okay, I guess it's time for a challenge. Can you find out how to plot the average weight of each species through the years? If you want to give it a go, pause the video. Otherwise, let's continue. Okay, so what we first need is the average weight of species. And what we do is we go to our data set from before, surveys underscore complete, and then using the pipe operator, we want to group by year and species ID, and then we want to summarize, and let's call it mean weight. So this is the new column, and that is based on the mean of the column weight. And then we're using a lot of the pipe operator here. We say use ggplot, and we don't need to put the data frame in because it knows we're using surveys underscore complete. So what we need is the aesthetics. So AES in brackets, year should be on the x-axis, and we want the mean weight to be on the y-axis, plus we want it to be a line graph, and plus we want it to be wrapped up, and we want this facet to be wrapped up in species ID. Species underscore ID. ID, and let's make it a beautiful theme. And I like the black and white theme that we used before, theme underscore BW. Okay, let's see whether I made some mistakes. Let's highlight the code. There we go. And run it. Oh yeah, you can see I made an error, can't add theme underscore BW. And that's because I forgot the brackets. Let's try this again. There we go. And now we have the average weight for each species ID over the years. Okay, and now let's come to the fun part, where we actually can customize our plots more and more. So we can change the axis and the title of the plot. And for that, we use labs. So the title, we say observe genre through time. The x-axis title should be year of observation, and the y-axis should be number of individuals. If we run this code, we can see we have now a title, and the labels on the axis are according to what we said. So that's what labs stand for, labels. We can also change the colors of the sex if we want. So if we don't want female to be this color and male to be with this color, we can actually change the colors as well. So we say scale color manually. That means we want to assign the colors to our factors, and then we just say values, and we use C for combine, in brackets M for male equals blue, and F for female equals green. Then we continue with our labels for the title and the axis and our theme. There we go, and now we have different colors for the sexes. Again, I would advise to choose colors that are friendly for everybody. And I will give you some links either below or in the supporting material. Okay, let's change the font size using the theme. We have again the same plots, a line graph wrapped up according to genus. We have our colors blue and green for the sexes, the labels for the title, the axis, the theme black and white, but now we want the text to be the size of 16. And now we can see it's very, very, very big. But if we make it bigger, all of a sudden it doesn't look as big as before. So it's a scaling thing on my little computer here. Let's make this a smaller again. And we can see that these numbers just do not look good, and like I said before, we can actually change that as well. We can change the orientation of the labels and adjust it vertically and horizontal. So this looks like a very scary big piece of code, but it's actually not as bad as it seems. So we have our function ggplot, again our data set, the y and the x and the y axis. We want the sexes to have different colors. We want it to be a line graph, wrapped it up according to genus. we want to have our own colors, blue for M and green for F. We want to have labels. We want to have a title on the top. The x-axis should be called year of observation. The y-axis should be called number of individuals. We want it to be the black and white theme. And then in theme, we say we want the color, the text of the color on the x-axis to be gray. The size should be 12. The angle should be 90 degrees. The adjustment, so that means you can move the text, the text of the scale. You can move it horizontal or vertical, and we just put 0.5 here, so it doesn't overlap with the little lines down here. And then on the y-axis, we want the color to be gray. The size 12. We want the angle that it's at, so that means it's horizontal. The 90-degree angle means that from horizontal it will be turned around to vertical. And then we want it italic, and the size should be 16 of the rest of the text. So this is the text, and the 600, 400 and so on that we want to be in size 12. Oops, that's too far. There we go. So now you can see the numbers have been turned 90 degrees. The text, so each genus is now italic. It's 16, the size is 16 for the labels and 12 for the scaling of the axis. Again, if we would change that a little bit, it would change, it would look very nice. And now let's save our plot or export it, and you have a few options to do that. You can either hit export, save as an image, or save as a PDF. If you click on image, you can also adjust the width and the height. Then you can say where you want it to be saved. But you can also write a little piece of code to save your plot, which I would recommend, because you can also adjust the DPI. So before you save your plot, you have to put it into an object. So let's call it my plot. And then we use basically everything that we used up here and put it into my plot, into the object. So we run this code, and we have created that object my plot now. And we can have a look whether we are happy with the plot. There we go. That looks good to me. And now we're saving it. So we use the function ggsave. And we want it to be in the folder fig that we created in the first module. We want it to be called observed_genre_time2.pdf. We need it to be my_plot, so the figure that we are creating or saving comes from my plot. The width should be 15, the height should be 10, and the DPI is 300, so the resolution should be 300. which is the standard for most papers, scientific papers. They require at least 300 nowadays. Okay, so we ran the code, and let's have a look. Files, figure, and we have created a PDF. And if we would click on that, it would be downloaded. We can also use different endings, so we could use PNG, for example. Run that piece of code, and now we have a PNG. So this is pretty good resolution. I'm quite happy with it. And this brings us to the end of the second module, how to plot your data with ggplot2. The whole script you should have by now, but you can find it on the EcoCommons website under Learn and Support. I hope this was helpful for you, and thank you for watching.